as groundwater conservation districts, we always hear about, using, balancing our regulations and balancing our management with the best available science. But that science includes collecting data. But what do we do with that data when we have it? How do we manage that data? Where do we store it? The panelists that are here with us today are going to talk to us a little bit about some of these intricacies and a little bit of overviews on how databases work and some of the other technological advances that we could be able to share and how to collect new data, whether it be electronic data or even some field data, and how to use that through databases. First up, talking about web-based information management benefits for GCDs, we have Michael Keester, who's a project manager and hydrogeologist with LER Water. He'll be joined with Dave Colvin, who's a project manager with LER Water. Mike began his career as a hydrogeologist in 2003, focusing on groundwater flow and determination of availability with respect to quantity and quality, as well as regulatory limitations. He specializes in applying numerical modeling and evaluation of aquifer hydraulics to provide quantitative assessments of groundwater availability, flow, and transport, including the determination of statistical uncertainty associated with the assessments and model predictions to better inform clients and meet their project needs. Throughout his evaluations, Mike has worked closely with clients to develop optimal operation plans for maximizing groundwater production to meet demands while maintaining regulatory compliance and minimizing the cost associated with the well field development, production, and maintenance. Mike has provided professional hydrogeologic consulting services to commercial entities, industrial operations, and governmental agencies. He's also provided expert testimony on behalf of clients during regulatory hearings regarding hydrogeologic condition and the potential effects of production from an aquifer. And Dave Colvin serves on LERE's board of directors and is a groundwater team leader responsible for providing technical leadership and coordination of diverse subject matter experts. He is a collaborative hydrogeologist with over 19 years experience in groundwater services, water resources, environmental science, and project management. Dave is currently focused on riverbank filtration, soil aquifer treatment, groundwater recharge, which is ASR and alluvial recharge, brackish groundwater, groundwater modeling, model uncertainty analysis, expert witness testimony, integrated water resource management, and sounds like just about everything water. He holds a Bachelor's of Science in Geology from Syracuse and a Master's of Science in Environmental Science and Engineering from the Colorado School of Mines. Dave is a licensed professional geologist in the state of Texas, Idaho, Wyoming, and Nebraska, and certified project management professional, and completed the Colorado Foundation for Water Education Water Leader Training course in 2011. He is active with the AWRA Colorado and the American Council of Engineering Companies. He is happiest while playing in the mountains with his wife and 2 daughters. Get your hands together for with Mike and Dave as they come up and tell us a little bit about database management.
All right, thanks, Bobby. As Bobby said, Mike and I are going to talk a little bit about the opportunities that GCDs have in groundwater data management. And I'm going to start at a very high level, and then Mike is going to bring it down and have some very specific examples about how data management can really get you looking forward. So, in one sense, we're all here because groundwater moves, and that's kind of a silly, stupid, water is wet type of statement, but it kind of relates to how we deal with groundwater data. And we all benefit from our forefathers in groundwater science. Take it a couple centuries back for Henry Darcy, or decades back for C.V. Tice, and those people were really trying to understand the basic principles of groundwater flow. So we don't have to worry about that stuff anymore. We can rely on their methodology to help our understanding. But thinking about how we use data, in some sense, we're trying to understand history. And so we're using historical data to try and understand what's happened in the past. And moving that forward into the present tense, we're thinking about how that relates to current conditions. As you all know, for the DFC process and 5-year cycles of planning, we're trying to get into more predictive modes of groundwater planning and groundwater understanding. So just like the old adage of, when to plant a tree, we want to be out there collecting data. And with today's world, the amount of data is just accelerating exponentially. And so we need to find ways to manage that and benefit from it. So thinking about that, we've been working on data management projects, particularly with groundwater data. And we've started to think about the different ways that you can categorize data management for groundwater data. As a little roadmap of what Mike and I are going to be talking about, I'm going to start with basic understanding of compiling data and some of the nuts and bolts of what we need to consider when we're pulling data into a system, and then how that data can be used to comprehend the groundwater system and your permittees and all of the related comprehension items. And then we'll start talking about how to use these systems to communicate. That's a really important aspect of groundwater, is being able to communicate it. And we have a unique struggle in that groundwater can't be seen, and we use black box models. And so it's inherently difficult to talk about, particularly to people that don't work with groundwater every day. So how can we use all of this data and communicate it clearly to the people that need to know about it? And then Mike's going to talk about how we can put all of that together into some specific examples of what can be done for data management with GCDs. So data compilation, it seems like a relatively simple task, but when you start thinking about it, this visualization here shows along the top are the more manual input modes. And so you've got your traditional computer, but now we've got all these mobile devices and getting information in there out in the field. Those are important improvements that have come along in the past 5 to 10 years. Then along the bottom there, we've got visualizations for kind of the larger data sets, those publicly available databases that you can pull down from USGS, from state entities, TWDB, from local entities, or even your own private SCADA systems or your own local data. So, trying to merge all of that into one database that's an important part of these data management systems. As I mentioned, the addition of mobile data entry is one of the newer aspects of this, but a really important one that when we're looking at these data management systems, we're trying to find any way to help you all do your work more efficiently, and obviously mobile data entry is one of those ways. So as you're entering data, back in the day when it was transcribed from forms or put into a spreadsheet, there's just a lot of room for error or misunderstanding. This form on the left here is a form that was created for well pumpage entry, and so we were able to cater it to specific users. So we could get a shot, a photograph of someone's meter and what it looked like, and then we're able to make their form look just like that meter so that it's a little more intuitive on the user interface for someone who might not be using computers a lot. So I think that's really helpful. And also in the lower left-hand corner there is the tabular data, so the historical summary of what's been put in the past so that the user can see that last month's reading was a certain reading, and if they put something in that just doesn't make sense, they'll be able to pick that up real time as they're entering the data. On the right, we're looking at validation. So as people were putting in their data, these databases now can do real-time validation, and if someone slips in an extra zero, or maybe they're entering data in the wrong units, the system's going to be able to alert them of that and kind of set them on the right direction. So these central repositories, those are the public databases that we talked about that obviously those are huge data sets, and we need to be able to digest them into a database that's going to be accessible to the user. So comprehension, pulling all this together is the first part of it, but then putting it together in a way that we can understand what the data means is the next step. And so in some cases, we just go to standard graphs, and that's kind of the first level of understanding, is taking all this tabular data from all these sources, put it together and make sure that it's right, and then put a graph together. This graph just shows pumping rate and water level. So pretty simple analysis, but a really important one, and one that you repeat on a very frequent basis. So being able to do that automatically is something that's just a huge time savings. So another way to start putting data together is to start doing calculations. And so this is starting to be a little more complex. This graph is showing some water quality ratios. So you're taking one data source and another data source, and you're just doing some simple math with it. So you're starting to move along into data analysis that helps you understand all of the data that's coming into your system. And this is starting to get into some of the ways that I think GCD data management systems can improve. And these are things that still need to be proven out, but this is a surface water example of taking some observation data out there. In this case, it's taking precipitation and stream flow and putting it together into a hydrologic model that's going to give you flood predictions. And so when you take those observations and run a model in the background, now all of a sudden you're starting to get into that predictive mode. And I think that that's where things are going, is moving from understanding history to understanding the current situation to now getting into understanding the future. And as I had mentioned before, communication, another key component of a data management system. We turn to graphs pretty easily, but what we've found is that with users that aren't as familiar with data analysis and that aren't sitting in front of a computer all the time, we can turn to some really identifiable data presentation, like the dials on your dashboard that people are really accustomed to seeing a speedometer and odometers. And so when you translate their pumpage into a speedometer type dial, then they understand where they are relative to their monthly allotment or whatever the measure is that you're trying to display. And with today's world of buzzing phones, I think that these systems just have to have the ability to push out alerts, because if something's wrong and your phone isn't buzzing at you, then sometimes you might miss the message and have to pay the price later. So with that, I think, Mike, if you want to take the mic and give us some real-world examples.
So thanks, Dave. So Dave's talked a lot about some of the kind of, like I said, the nuts and bolts of the projects, some of these tools and some of the work that goes into them and how they can be used. But I wanted to turn to a few some examples of how the data can be used and putting all of these things together and how we can apply some of these tools. So this first example that I'm looking at here, it's a project that it's one that Dave talked about, one of the parts of it there, where we're able to take that meter data and take it in through either a desktop or a mobile interface, or also through telemetry, just getting that data automatically uploaded into the system. And the interface, it included those validation steps to help ensure that that data that's compiled it's as accurate as possible. And as you all know, if you don't get correct data, then those interpretations from that data are also going to be, well, a little suspect. How many times have you looked into a database and gone, why is my well located over there in the Atlantic Ocean? Or say, in a little bit better case, in a county adjacent to where it's supposed to be. But, well, and I ran into this, for example, very recently, had a situation where an entity came to us for some help on a project. Now, the entity, they had this well, and it had a transducer set in the well, and it was installed in order to automatically record those water levels. And it had been doing this for about 2 years, that those water levels were being recorded and put into that management system, but the data management system that they had, it didn't have that validation step in there. So we started looking at it, and just something's not right with this data. Things are way off. Things are way off compared to where they should be in other wells nearby, and we could tell that it was inaccurate. And what did turn out that when the installer had put that transducer in the well, they had just set one of the settings incorrect on it. So because that was set in there, and because it kept being recorded, and there wasn't that validation step in there, had 2 years of data that essentially we had to be discarded. They could potentially have been seen much earlier, or found much earlier. So. But looking back at that meter reading and that information there, we have a lot of data that gets compiled. We feel really good about it. And now to help us comprehend that data, those readings automatically get converted into some pumping volumes. In this case, for example, end acre feet. But for those months that are incomplete, or let's say there's a data gap, say there was an equipment failure, we're able to build within the tool here to help with the comprehension of the data that is able to project out in order to make complete months of information and provide an estimated total. The next step there is then to take those pumping amounts and then use those as inputs for models that are built within those tools in order to provide some instant feedback to users regarding the impacts of that pumping on surface water sources due to both past and projected future pumping. So how much depletion was occurring of those surface water sources. The results of that modeling, they get communicated to the end user there through this table, provides them an estimate of what those depletions are, and as you know, one of these tables, once we have this, it can be easily translated into a graph or a chart just to really give a very easy way of communicating to the user what's projected to occur or what's happened in the past. So thinking about that previous example, we were looking at a situation where we had these meter readings being automatically uploaded or imported into the database. Well, what happens when you have a situation where you're trying to figure out how much pumping has occurred in the past? Well, if you have a good water level monitoring network, then one thing that you can potentially do with your data management system is use that water level data along with some of the information from the aquifer to find out how much pumping occurred in the aquifer. Now, in many of the Texas aquifers, changes in those water levels are due primarily to production. So by taking that information and with those numerous water level monitoring networks that we have, both from the Water Development Board or from districts, we feel like there's ample measurements to inform us of the pumping in those recent years. And for every aquifer in Texas, that we do have at least some understanding of how water moves through that aquifer and how that aquifer responds to pumping. For most of the aquifers, that understanding has been taken and it's been compiled into some type of numerical model or a GAM. And the very nature of these types of models makes them very well suited for incorporation into a data management system. So essentially, like looking, for example, in this one, we're able to take those input files, or at least the numbers that make up those input files for these models, and bring them into that data management system, and then we can use these models and the aquifer properties that are stored within them, along with those observed water levels in order to develop an estimate of pumping that occurred. And this process of estimating pumping based on water levels and aquifer properties, I'll be honest, it's not anything new. When we are developing a GAM or developing a model, that process of calibrating those models, we frequently use those historical water level changes along with what we know about the aquifer to include how much pumping might have occurred in the past. And that becomes one of those things that we're trying to figure out when we do the calibration of the model. And through that data management system, we can take those estimates of pumping along with reported pumping and then automatically maintain an up-to-date model. Part of that could be, let's say we take those information, we take those calculations, we take those functions that are built into the system. We're basically performing automated calibration of the model on a regular basis, on a scheduled basis. It could be monthly instead of every 10 years or so. We could continually do predictive uncertainty, find out how wrong our models are, or DFC uncertainty. And another thing we can do is figure out, okay, with this information that I'm gathering, I continue to do these other functions in the models and use this system itself to find out where is going to be the best place based on that modeling and based on that information I gained from it to put that next monitoring well. In other words, where to get the most bang for your buck. It could also be used by GCDs to help inform managers of areas where their unreported pumping may be occurring, or the verification within those bounds of uncertainty and of the reported production. And the results could also be incorporated into those future updates, into future joint planning of DFCs. So thinking about the DFCs, you probably heard just a couple of hours ago maybe where Javon was talking about monitoring well networks and assessing DFCs and compliance with DFCs. Well, within a robust data management system, those compiled water level data and the numerical model outputs, these are easily and readily compared to evaluate status of an aquifer relative to those adopted DFCs. As you can see on these charts that are up here, we can quickly visualize the modeled and the measured water level data, get a quick look on how well these two compare to each other. Looking at those, you can see that both wells, you look at the measured water levels, they appear to show a declining trend from start to bottom, though we do see the last couple of years water levels rising. In the real world, keep in mind, of course, that pumping with an aquifer is inconsistent. But when we look at modeled water levels, you see this nice steady decline. Well, that's because within the model, pumping doesn't change for this particular scenario anyway. But what we need to do is to use this data management system to find an efficient way to effectively compare these data sets. How does one compare to the other? Now, I'll be honest, I agree with what Javon was talking about earlier. If you happen to miss it, one of the things that she mentioned is, there are a lot of ways to look at DFC comparisons. So, and to answer that question. And you're going to hear some more tomorrow morning even. There's a session talking about DFCs and compliance. Well, I'm going to talk to you about one possible method, so one way to look at them. But using those measured water levels, you can see that just using the measured water levels, we can quickly look at the trend of how those water levels change and what that dominant trend is to help us comprehend and get a better idea of how the aquifer is responding to pumping or to other inflows and outflows. Looking at the dominant trend for every one of the water level measurements up there, we can see, yeah, it looks like those water levels have been declining over time. However, we're considering DFCs in this case, so we're looking at, well, the model, it has to calculate its DFC, and the evaluation was done from a very specific day and time in the past. In this case, midnight on January 1st, 2010. So we set that as the date from when things will be calculated and when trends will be computed. Like all validation steps, like the validation steps that are applied even to the compiled data that we were talking about, and to ensure that those data are accurate, the GCDs, you guys can also set up these rules to constrain the evaluation of water level data. Those rules are going to recognize when there's a large gap in data and apply corrections or methods, functions to account for those gaps in the data. In addition, those rules can constrain the evaluation to just be the baseline data of the DFC. and capture a trend that, it may not be readily observable when you first just look at that raw data, such as, in this case, for example, for well A, that there's a little bit of recovery from that January 1st date, or in well B, that it's a continued slight decline. So then you need to find a way to communicate that data. Well, data from wells, they can be evaluated in the background. You don't have to see those previous slides that I just showed you. However, they're like many complex evaluations, you've got to find a way to communicate those results that are effectively, and that can be the real challenge. And in this example, for example, I needed to find a way to take data from a lot of wells, evaluate that data, compile the results, and provide a very straightforward way of answering a question that is going to be most important to a lot of stakeholders. Where are we in relation to the DFC so that I know when I might be cut back? Well, for this particular summary, I looked at a little over a dozen wells and applied several rules. It's constrained to a county, but applied several rules to calculate the average drawdown in the aquifer, and based on those measured water levels. Rules that were applied, they accounted for the gaps in the data so that those were taken care of. It looked at what area a particular well may represent, and it accounted for the DFC, the baseline, that single date and time in the past. The summary here gives that GCD manager or stakeholders where they are, gives them a real quick, easy way to find out where they are in relation to the DFC, and that you can take a look at that chart, readily see what the DFC is, exactly see where you are today, and where you would be in 2070 based on those real-world measurements. Keep in mind, the chart's easily modifiable to take advantage of those multiple methods so that you can present not just one answer, but all of the possible answers, all of which could be correct, of course. So I'm going to close by just talking to you a little bit about how these tools can also be applied even at a larger level, looking at the GMA joint planning process as a whole. Now, as you're all aware, there's a lot of groups that are working together during that joint planning process, and efficiently soliciting input from those groups and from those stakeholders, that can be a real challenge. Yet, that input's crucial for adequately addressing those 9 factors that you're required to consider. Well, setting up a relatively simple web-based data management system would allow those GCDs that are spread throughout, throughout a GMA to more easily direct stakeholders, for example, to a single location to provide input. Specific forms can be set up that allows feedback through a mapping application. The GCDs could even be able to better understand if the perspectives are geographically biased. And what I mean by that is, let's say there's some stakeholders and you have all of this input, but a lot of the input says they want more drawdown, more production. Another set, less drawdown, less production. Well, by having it within that mapping application, you can see if the more production ones are in a certain part of the county or the district, the others are located in another part, and it would give you the potential to set up DFCs that can honor the wishes of both constituents. So looking at it geographically across that way. And much like the solicitation of stakeholder input, technical collaboration can also be a challenge during the DFC process. Well, a web-based system like this could also provide that single location for providing that technical support to the GMA that collaborate in that open and transparent manner. For example, as we were discussing a moment ago, these models, they're frequently used to evaluate the potential DFCs. They can also be part of the web-based system. So once that system is set up, potential pumping amounts and locations can be brought into the system. They can be added, they can be removed, they can be modified. Model runs can be conducted, and those results pretty quickly evaluated within the system itself. Provisional results from the modeling could then be immediately visible on that web-based application. The potential for that more rapid feedback from the modeling scenarios, the scenario inputs could be more easily and quickly adjusted to help, really just to help enhance that understanding of how that aquifer responds to future production and to inform those who are responsible for adopting aquifer DFCs. Using a web-based system during that joint planning effort, it would certainly increase the transparency of the process to the stakeholders. And I know every one of the GCD managers and board members out here, you do everything you can to make this get stakeholders as involved as possible, make it as transparent as possible. But as you all know, there's times that you just can't make it to a meeting or can't make it to a joint planning meeting. So by providing a link that they can go to and access where they're going to see all of this information, for example, even with like they're doing here with the live streaming, it makes that process that much more open and that much more available. So with that, I know that I had another 30 minutes, but I just wasn't going to be able to talk that long. So Dave and I have covered a lot of information, we believe that these tools can really help you out as far as making life a little bit easier for GCDs, making things more efficient, and increasing that efficiency and expanding their opportunities for understanding your aquifers. So with that.
Gentlemen, thank you very much. Is there any questions on the floor? I know we've been promoting a lot of questions through the Twitter feeds and whatnot, but since this is actually being recorded and not live streamed, I don't know if people on the other end are really asking Twitter questions, but we'd like to invite anybody on the floor, if they've got any questions in person, you're more than welcome to ask those questions now. Yeah, okay.
Hey, Mike, just out of curiosity, folks you visit with, do they really, for the most part, looking at 50 years of information to try to determine the attainment, or is it taken in smaller chunks of time to really analyze it?
As far as for DFC compliance? The way that I've seen some of them looking at it is they do tend to take it in smaller chunks and look at it in those smaller increments. And that's one of the ways it can be sliced up. The DFC itself tends to be adopted for a long period of time rather than on the shorter chunks. So with that, we have to try to find a way to take all of that data and find a way to project where we would be at the same time in the future in order to assess compliance with it. For example, I'm working with an entity that's a potential, they're working on a groundwater production permit. And one of the questions that they have is how are we going to be assessed in the future with regards to what the DFC is. So using this type of example is what I've shown them is one of the ways that it could potentially be looked at. So.
And I'll probably add to that, that's probably, I know we heard from other people, were talking earlier, panelists on another earlier session about groundwater monitoring and, real data on the ground versus what a model can provide. And these databases allow for you to input that data, correct? And
right.
Have a single location for you to find that modeled data and real-time data put together.
Right, you get that one location to compare both of those, all of the information from both, as well as build in functions to look at it so that you can assess, okay, it's somewhere looking at it the multiple ways, for example, the way Javon looked at it for Post Oak, and I know there's other ways out there that are being looked at in order to go, the answer is somewhere between plus or minus this value of X rather than looking at a single number. So.
Yes, sir.
I imagine you can identify when you maybe change methods of measuring water levels,
Mm-hmm.
or if the water table has dropped below the top of the stream and things like that.
Right.
Maybe throw things off.
Yes, you can look at that, and what that should it shouldn't really throw things off too much because it does change the dynamics of how the aquifer responds. But when you start looking at just a water level trend or changes in water level over time, then that ends up being accounted for, and especially when you start looking at what's the dominant trend and the change from this point to this point in time. So.
Any other questions? All right, if not, thank y'all very much. Okay. Mike, appreciate it.